Okay, so let's have a look at a few more examples on pulleys. Now, when we talk about pulley questions, there are basically two types of pulleys you need to know. So the first type of pulleys you need to know is called the simple pulley. So let's look at a couple examples of how we can draw diagrams and also label all the forces on a simple pulley. So type 1 simple pulley. So for example, you could have a pulley hanging on the ceiling, and you could have a light inextensible strings attached around the pulley, and on one end of the pulley you could have a box, and on the other hand you could have another box. So in one of the box, let's say the box on the left hand side, it has a mass of 2 kilograms, and the box on the right hand side has mass of 5 kilograms. Okay, so now let's have a think. Well, imagine if at the very beginning both boxes being held in position and nothing is moving. Okay, and when I say, for example, if both your hands are under both the box, imagine that you pull your hands away at the same time from the bottom of both boxes. What would happen? Well, you can see here on the right hand side, the box has 5 kilogram mass, and that is heavier than the box on the left hand side. So what that means is when I take my hands away, this box on the right hand side will start to move down towards the ground. So that means its acceleration downwards. Okay, and what would happen to this box, which is only 2 kilograms? Well, this box will then get pulled upwards. Now that's because those two boxes are connected by the same string. Okay, and because we said it's light inaccessible string, so that means this box on the left hand side will get pulled upwards, but with the same magnitude of the acceleration. So for example, if the right hand side, the 5 kilogram box is going down at a rate of 2 meters per second square, that means this little box here on the left hand side will also be pulled upwards with the same acceleration, but just in a different direction. Okay, so right, so let's have a look. How can we label the forces? Well, you have to think each object separately. So for the 2 kilogram box, we have the weight acting downwards, and that would be weight equals mass times by g, so that's just 2g. Okay, so now the box is connected by the string, so that means there will be a tension in the string. So let's say it's just T. Okay, so those are the two only forces acting on the box, which is 2 kilograms. So let's have a look at the 5 kilogram box. Again, it will have a weight acting downwards, and that would be 5g. And there will be a tension in the string. Now, what would be this tension? Well, as we said, both boxes are connected by the same string, and it is a light inaccessible string, and the string should be taut as well. So that means the tensions throughout the string should be exactly the same. So now, imagine here, on the right top of here, if the string is touching the pulley, okay, at that point, that we're experiencing a tension here as well. So the tension is pulling the box up, which means there will be a tension pulling the string downwards in this direction. So that means here there will be a tension pulling downwards by this box as well. So that means this tension will be T as well. Okay, so you just need to remember, if it's the same piece of string, the tension in the string will have to be the same. So you can use the same letter T to represent all the tension. Okay, now normally in a question, those two tension, this T and the T on top of here, you don't need to consider them because they cancels out. Okay, so you only need to consider the tension acting on each object. Okay, so if I draw another diagram, for example, again, it's a similar thing, but this time, let's say we have a box over here, and that is 4 kilograms, and a box over here on the right hand side, and that's only 1 kilogram. So again, imagine at the beginning, both boxes are being held still. When I take my hands away, what's going to happen? Well, hopefully now you'll realize that because the box on the left hand side is heavier, so that means when I release both the box, this box will start to go downwards. So we have acceleration down, so that means this box will get pulled upwards because it's lighter. And remember, the acceleration throughout the same string will be the same, A and A, but just with different directions. And how do we draw the label all the forces? Well, again, always start with the weight. W equals mg, so it'll just be 4g. And it's attached by a string, so there must be a tension, which is T. So over here, the 1 kilogram box, again, we have weight, which is 1g. And because it's attached by the same piece of string, so the tension will also be T. Okay, so they are all the forces acting on both the boxes. Okay, so in summary, so if I just draw a generic diagram of a simple pulley, let's say, so here on the left hand side, we have a box with mass of M1. And on the right hand side, we have a box of mass M2. And given that, imagine if M2 is greater than M1, so M2 is heavier. Okay. Now, when I release both the boxes, M2, this box, will go down, and M1, this box on the left hand side, will be pulled upwards. So this is how you should label your acceleration. And the force acting on each box for the M2, you have the weight, W equals to mg, so it'll be m2g. And the tension in the string, that's just capital T. Weight or the force acting on M1, again, that would be the weight, W equals to m1g. And the same tension T acting directly upwards. So that's it. So this is the generic kind of diagram. Okay. Now you do also need to be careful for simple pulley. Okay. When something's being released, okay, after the block's being released, certain things could happen. Okay. So again, let's have a look at this generic diagram. So imagine that there is a ground on the bottom here. Okay. Now, imagine the string is long enough, so when I let both the boxes go, M2 is heavier, so it will start to go down towards the ground. Now, after some time, this box M2 must hit the ground. Okay, and M1 will be pulled upward to a certain point, but until the point when M2 reaches the ground, M1 will have the same acceleration as M2, so the same magnitude, okay? But what would happen after M2 hits the ground? Okay, so that's the second stage. Because when M2 hits the ground, there is no tension in the string because there's nothing pulling M1 anymore. M2 already hit the ground, nothing's pulling, okay? So from that point, okay, you have to rethink about the force and acceleration for your M1, okay? So let's see if we can do another diagram just to kind of clarify those two stages. Drawings. Okay, so let's write down our two stages. Okay, stage 1. M2 starts to fall. Towards the ground. So what is happening when M2 starts to fall towards the ground? Well, there's a few things happening here. Okay, so let's do some bullet points to summarize. So firstly, our M2 and M1, they will have the same acceleration, but in different direction. Okay. Now, second point, there is a tension in the string. So there is tension T in the string, or you could say there are tensions attaching to each box. Right. Something else you need to know, which can be quite easily forgotten in exam, is, well, if you think when M2 starts to fall, okay, the distance M2 traveled will also be the same distance M1 traveled because they're being attached by the same piece of string. So that's quite an important point you need to remember. Okay, so M2 and M1 will travel the same distance. So for example, if we take M2 maybe 3 meters until it hits the ground, that means throughout that time, M1 would be traveled upwards by 3 meters as well. Okay? All right, so this is when M2 starts to fall towards the ground. Okay, right. Stage 2. So stage 2, that's when M2 hits the ground. Okay, so when M2 hits the ground, well, there's nothing we need to do for M2 now because it's on the ground. Okay, but as we talked about before, what is happening to M1? So there will be no tension in the string anymore because M2 is not pulling anymore. So there is no tension. Okay, so you may need to draw a separate diagram with all the force and labeling, okay, but without tension. Okay, now, second point, although M2 is not pulling anymore, okay, M1 will still travel for another distance, okay, until, because if you think at the point when M2 hits the ground, M1 was still traveling with a certain speed or velocity. okay? So that would become m1's initial velocity. And at some point, after a certain time, m1 will travel another further distance until its velocity reaches to 0, and then it will stop, okay? So let's write this down. Now, next, so m1 continue the movement until its velocity becomes 0. Okay, so you can see here we'll have our Suvert equation or formula involved at some point. Okay, so I think that's all the notes. Maybe we could have a look at a question. Let's just use some random numbers, okay? Right, so let me clear this page. Right, so for example, okay, so let's say around this pulley we have a box and has a weight of 2 kilograms. I kept saying weight, it should be the mass. Sorry. Okay, and then let's say over here we have another box which has weight 5, mass 5 kilograms. Okay, and here's the ground. And let's say if it's given that the height between the 5 kilogram box and the ground is, let's say, 2 meters. Okay, so our question is, let's say, part A. Imagine that both boxes are being held still at the very beginning. Part A, find T, find the time taken for the 5 kilogram box to hit the ground. And then part B, how far in total did the 2 kilogram box would travel until it stops. Okay, when I say until it stops, I mean at the point when the velocity is 0. Okay, we're not considering the situation where the box will fall down again. Okay, so we're not considering that. Right. Okay, so I guess there must be some assumption given in if it's an exam question. Okay, you will say it's a light insect string, and also the string will be long enough for the 2 kilogram box to travel upwards as well. Okay, right. So let's have a look at this question. So firstly, let's label all the forces. Okay, now for 2 kilogram box, we have the weight, which is mg, so that's 2g. And there's the tension, which is T. For the 5 kilogram box, we have the weight, which is 5G, and tension, which is T. And straight away, we know that this box is heavier, so we'll have acceleration travel downwards. This box is lighter, so it's going to go upwards, but with the same acceleration. Okay. Part A, let's find the time taken for the 5 kilogram box to hit the ground. So that just means that the 5 kilogram box have traveled 2 meters, isn't it? Yeah. Now, the thing is, well, I need to know this unknown here, isn't it? Yeah. So I need to know what would be its acceleration. Right. So let's write it down. For 5 kilogram box, if I want to work out the acceleration, I have to use Newton's second law, which is F equals to ma. So let's think about the resultant force. Okay. Now, since A is traveling downwards, so we're going to say downwards is a positive direction for this block. So that means the weight would be the positive. So we have 5g. And then t is going upwards, so it's negative. So we're going to do 5g minus t. And that will equal to ma, and m is 5. So it'll be 5a. Okay, now I can't solve a yet because we have this t here. So I need another equation. Now we need to think about this 2 kilogram box. Again, we're going to use F equals ma. Now this time, now be careful because we are considering forces on different objects. We're going to treat them differently here. Okay, so here in this situation, I'm going to take upwards as positive direction because acceleration is going upwards. So in this case, t is going upwards, so t is actually positive. And the weight is going downwards, that means weight would be negative. So I'm going to use t take away 2g. And that equals ma, and m is the new mass, which is 2. But remember, the acceleration is the same, so we can use a. Okay, so here you can see we've got 2 equations, 2 unknowns, and there's no way the question asking for the tension. So if I can get rid of t, I can work out a. Okay, so let's say this is my equation 1, this is my equation 2. So why don't we make t the subject in equation 2? So equation 2, I can say that t would equal to 2a minus 2g. And we're going to substitute this equation into equation 1. So let's substitute into equation 1. We will get 5g minus t. Now remember, t is being replaced, so we have to put a bracket. So replace t with 2a minus 2g. That equals to 5a. Open the bracket, don't forget to change the sign. So we have 5g minus 2a plus 2g equals to 5a. Okay, have we done everything right? Let me just check. I think so. All right, so now, yeah, I think I've done everything right. Okay, right. So now we can rearrange to get 7g equals to 7a. So that means a would equals to g. Okay. Right. Now, then we can work out the time. Let's write down as our SUVAT. Distance traveled is 2 meters. What is the initial velocity? Well, remember at the beginning we said both the blocks being held still, so u is 0. I don't know what's v. I don't know what is speed when you hit the ground, so forget about that. I do know the acceleration is g, and we're looking for the time. So which survey equation do we need? That doesn't involve v, so that would be s equals to ut plus a half at squared. So that would be 2 equals to, okay, so that's convenient. That's just 0 plus a half times by a, which is g. Let's replace it by 9.8 and times by t squared. So we've got 2 equals to 4.9 t squared. So t squared would equal to 2.45, and taking the positive of the answer, square root of 2.45, we will get the answer is 1.57 seconds. Okay. Right. Now, that's part A done. Let's have a look at part B. Okay. Almost there. Okay. That's perfect. Okay, so right, part B. How far in total did the 2 kilogram box travel until it stopped? So remember, there's 2 stages, okay, for the lighter box. Stage 1 is when the 5 kilogram box being released and it's going to travel towards the ground. So that means during that time, the 2 kilogram box would travel the same distance as the 5 kilogram box, which means it would travel 2 meters. So stage 1, you already traveled 2 meters. Now, the problem is, how far did it travel in stage 2? Well, so remember, when the 5 kilogram box hit the ground, it would not pull the string anymore. So if I draw another diagram for my 2 kilogram box, there's only one force acting on it, which is the weight, and that's 2g. Okay, now, so there's no tension here. Okay, so that means what would it be? Well, what would be its acceleration then? Well, do you remember before we have worked out the acceleration, right? We can't use the acceleration anymore. When there's nothing pulling on an object, basically the only acceleration will work on it would be the gravity. So really what is happening here is that we have an acceleration going actually downwards. Okay, now maybe that's quite confusing. So if we say the movement, okay, say we still travel upwards, but we just need to know our acceleration now is negative 9.8. Okay, the reason why I'm using upwards as the positive direction is because the movement, so the displacement is still going upwards. Okay, so it's just a little bit easier when we use our SUVA. So let's write out as our SUVAT. Distance is something we're looking for. U now, what would be its initial velocity? I don't think we'll work it out. So remember, the initial velocity at this stage would be the final velocity for the stage 1, but unfortunately we didn't work it out. So cross it out, we don't know. Now we do know what would be its final velocity because that would just be when it becomes 0. And it would have stopped, well, basically at that time, it would have stopped moving upwards, okay? Right, acceleration, that's negative 1.8. And we don't know the time actually. Okay, so maybe I shouldn't wipe it off. We'll probably need to work out the u, isn't it? Because I don't know the t. Okay. Right. Let's go back and think about my u. Okay, so when the 5 kilogram box hits the ground, what would it be its velocity? Right. So SUVAT. At that time, it traveled 2 meters. U was 0. We're looking for V now. I don't really remember what did we say before? G. So that's 1.8. Time we worked out before is 1.57. Okay, so we can work out V. So why don't we use this formula? So V squared equals to U squared plus 2AS. So sorry, this one is I'm going back to use my part A. Okay, it would be better if I actually didn't clear up my notes for part A. But hopefully you have written it down so you can go back and have a look for numbers there. Okay, right. So let's work out V. So V squared equals to U, which is 0, plus 2 times by A, which is 9.8, and times by 2. So V squared equals to 39.2. So the final velocity is 6.26. Now remember, both boxes being connected by the same string. So if the final velocity for the 5 kilogram box is 6.26 meters per second, that means this will also be the final velocity for the 2 kilogram box. Okay, so this is all for stage 1. Right, now, okay, great. So when the box hits the ground, the velocity is 6.26. So that will now become the initial velocity for stage 2 for my box, 2 kilogram box. So let's put it over here. So now I know my initial velocity is 6.26. Okay, so that's better. So now I can work out S. So I have SUVA. So again, it's the same formula. I had a squeezing on here on the top here. Okay, so V squared equals to U squared plus 2AS. So V squared, that's 0. U is 6.26 and then squared plus 2 times by acceleration is negative 9.8 times by S. Okay, so now that means our 6.26 squared, that's 39.2, and here 2 times by minus 9.8, that is 19.6. Now because it's negative, so I'm going to move the whole thing to the left hand side, make it positive. So we have 19.6s. So S equals to 39.2 divided by 19.6. And that is, oh, 2. Great. Okay. So that means stage 2. After the heavy box reached the ground, the 2 kilogram box continued to move upwards by another 2 meters. So altogether, in total, we have traveled 4 meters, assuming it is possible. Great. Right. Okay, so that's our first type. Okay, it took us a little bit longer, but that's okay. Let's have a look at the next one, which is our type 2. So type 2 is when you have a pulley attached to maybe a table. Okay, or some kind of surface. So for example, let's say this is the table, and then you have a pulley here. So what normally happen would be you have a string goes parallel to the table and then go down, and then you will have an object hanging down here, and you also have an object over here resting on the surface. Okay, right. So let's say this box has mass m1, this box has mass m2. Let's label all the forces acting on it. So we have weight, which is m2g, and we have tension, which is T. And over here, we have tension T. Now, okay, yes, we have the weight, M1G, but what else is acting on this box, which actually doesn't exist for our previous example? Well, in this case, because the box is resting on a surface, that means there must be a normal reaction force acting upwards. So the R and the normal reaction force R and the weight actually will cancels out in the vertical direction. Okay, so when we have pulley attached to a table in this kind of case, you normally don't need to consider the R and the weight in this direction. Right, but you do need to be careful is that something will have to go in the opposite direction to T, the tension, okay? And that's normally the friction between the object and the surface. And then we use a little f to represent friction. Okay, so what would it be happening? So imagine at the very beginning, everything being held still. Let's say if I release the box M2, and M2 is quite heavy, so it will start to pull the string downwards. So it's going to accelerate downwards. Okay, now when I pull the string here, what's going to happen to this box M1? Well, the box will get pulled towards the right hand side. So this is the direction with the same acceleration. Okay, so that's basically it. Okay, right. One thing you have to be careful, if it's in the exam question, and if you mention the word equilibrium, okay, so if it's in equilibrium, then you would know your A is 0. Okay, because equilibrium means, well, everything's stationary, staying still. Okay, so A is 0. Or if the box is moving, so that means you will have an acceleration. So it must be given in a question. If given acceleration, and then you can find the friction force, okay, by looking at, well, from here you could work out T, and then you from the T you can work out the F, because for this box, right, acceleration is basically acting in the horizontal direction, and the only two forces acting in the horizontal direction would be the tension and the friction. Okay, so now let's have a look at a question, because in some of the exam questions, they don't really give you a diagram. Okay, so you need to know how to actually draw the diagram and label all the forces. So let's have a look at one question. Right. So here it says particles P and Q of mass 0.45 kilogram and m kilogram respectively are attached to the end of a light inextensible string which passes over a small smooth pulley. So what does that mean here? Small smooth pulley means that you can basically ignore the weight of the pulley and there's no friction between the string and the pulley. Okay, and then the particles are released from the rest. Right, so from this question, we know that this is the first type of the question. Okay, it's not attached to the surface, so it's a simple pulley. So straight away, I know that I could have a pulley, looks like that, and the string attached to it, so it goes around it like that, and I have two particles, one particle P with weight, sorry, mass 0.45 kilogram, so P, and actually, you know what, maybe I shouldn't write so many things in the box. Okay, let's just say that's P. And then we also on the other side has Q. You can then say MP is 0.45 and the Q unfortunately don't know. Right, then it says the particles are released from rest with the string taut and both particles 0.36 meters above the horizontal surface. So that means they've been held at the same height. Okay, so this distance here are both the same, they're both 0.36 meter. Then it says Q descends with acceleration 0.98. Aha, so here this is quite important. Q starts to travel downwards. So we can then label on the diagram acceleration downwards, and that's 0.98. What can you tell of the mass of the box? If Q starts to travel downwards, that means it must be heavier. So when you work the answer later on for M, you should get an answer which is greater than 0.45. Okay, now also we can start to actually label the weight. Before we do that, I can also label here, because they're being attached by the same string, so they would have the same acceleration. So P would actually travel upwards with acceleration 0.98 as well. Okay, so let's draw the forces on the diagram. So for P, there will be weight, which is mg, so 0.45 g, and the tension T going upwards. For Q, also there's a weight, which is mg, we don't know m, that's something we're looking for, and the tension T upwards. That's it. Okay, so then it says when Q strikes the surface, it remains at rest. Calculate tension string where both particles are in motion. Okay, so we're looking for tension this time. Right. Right, so now let's consider the box separately. So box Q is going downwards. So again, we have to use F equals ma. If it's traveling downwards is the positive direction, then weight would be in the positive direction. So that would be mg minus T equals to ma, so it will be 0.98. m, because m is the unknown, okay? And then for p, we're using upwards as positive direction, so now t is positive, so be t minus the weight, which is 0.45 g, and that equals ma, so it's 0.45 times by acceleration 0.98. So from the second equation, you can see that I can work out t straight away. So t, because g here is 0. So g here is 9.8, isn't it? Yeah. So with that point calculator, work it out. So I got my answer for T is 4.851 Newton. Okay, now when we work out the tension, I can put it into the first equation to work out the mass for Q. So that is part B actually. So we've got mg, so g is 9.8, so m times by 9.8 minus tension 4.851, that equals to 0.98 m. Okay, so rearrange, we would get 8.82 m equals to 4.851. So m equals to 0.55 kilogram. And do you remember at the beginning of the question, we said Q start to travel downwards, so that means Q must have a bigger mass, and our answer cannot be 0.55, which is greater than 0.45. So that means our answer should be correct. Okay. Now, part C, calculate speed at which Q strikes the surface. So that's when you have to use your pseudo equation SUVAT. And S is distance traveled, which is 0.36. U, remember at the beginning, they were not moving, so U is 0. We don't know the V, that's what we're looking for, the question mark next to it. And A, so let's just say Q, so that means A would be 0. Then A, time unknown, cross it out, so we can work out V. We have to use V squared equals to U squared plus 2AS. So V squared will equals to 0 plus 2 times by 0.98 for A, and S is 0.36. So let me put a calculator. And I have got my answer for V, that is 0.84 meter per second. So that is for part C. And then part D, calculate the greatest height. So, okay, so this is exactly what we talk about. You're going to have to think about stage 1, the distance P traveled when Q hits the ground. So that would be basically 0.36. Okay, so stage 1, 0.36. Stage 2, that's something you actually have to work out, is when Q hits the ground, nothing's pulling P anymore. So how far would P travel? So you need to use another super equation and work it out. Okay, so I've run out of space here, but I would really like you to try this question yourself because it's very similar to the previous example we've done. Okay, and you can use the answer in the back of the book to see if you manage to get the answer. If it doesn't work, let me know straight away and I will try to help you with this part. So hopefully this helped you a little bit more with Pulley. Okay, and again, please do email me again if you have further questions, and I'll be very happy to help you again.